Hello, everyone. Great to see all of you. And let's wait for probably 1 or 2 minutes before we get started. And this has been a really busy week. A lot of exciting things are going on in the world of AI. And the one event is that the AI pen seems to be on the market. So starting from a few days ago, I see someone posting a YouTube video showcase how the AI pin works. And a lot of critics, some people are really excited, but others feel disappointed. I think the market does have a very mixed view, regarding the performance of the AI pin, which is expected. And the OpenAI, I think, is in discussion with some venture capital to launch their own hardware, of course, powered by large language models. And they're trying to raise significant money to make the product. So everyone is trying to take the share of iPhone because that's been over 15 years dominating the market, and it's probably the time to replace it with the next gen product. And I haven't used Cloud 3, but I heard many good things about Cloud 3, and some people posted on Medium, making a head-to-head comparison between the GPT-4 and Cloud 3. There are different versions. There were Sonnet version and Ultra version, and it seems like the Cloud 3, based on many benchmarks, beat GPT-4 by a margin. And also the cost is about a third of GPT-4. So down the road, I guess there are more competitions ahead. And we'll see whether people start to switch to Cloud 3 by Anthropic rather than staying with GPT-4 model. Okay, so great. I think we should get started. Today we are extremely thrilled to have Zach presenting the evolutionary algorithm or genetic algorithms. And many of you, and including myself, are very new to this idea. And we most likely we know AI from supervised learning and to some extent unsupervised learning and then reinforcement learning. But the genetic methods or evolutionary method is also part of the AI family. And it has a lot of potential to optimize our solutions and searching in higher dimensional spaces to look for hyperparameter tuning, etc. So there are a lot of exciting things going on in that subdomain, but unfortunately not known much by the mainstream AI community. So I'm really happy that we have an in-house expert in that method. So without further ado, I would hand it over to Zach. Maybe, Zach, if you could make a brief self-introduction, and then we can get started.
Sure, thank you, Dr. Ang. So I'm going to share my screen. Can you guys hear me clearly?
Yes, we can hear you.
Yes.
So I guess I'm sharing the, okay. Yeah. And good evening, probably good afternoon, good morning, everyone. And thank you for being here today. First of all, I'd like to extend my thanks to Dr. Ang for giving me this wonderful opportunity to share my experience in evolutionary algorithm with you guys. And it's my privilege to be a part of this AI interest group. And I think this is a place where we all come together to learn, to share, and stay on the cutting edge of new AI technologies. So before I dive into today's topic, let me share a little bit about myself to give you some context. So I earned my PhD in China in applied mathematics and later joined WashU as a postdoc. Later, I was promoted as the research track instructor in OBGYN department. But my current research focus in developing new biomedical imaging systems to provide 3D visualizations in obstetrics. Our goal is to reduce preterm birth and improve labor management during childbirth. So my main expertise lies in intersection of applied mathematics, biomedical imaging, and some experience in machine learning and AI. So I'm also a husband and a father of 2 boys. I've been living in St. Louis for more than 7 years. Welcome if you would like to chat with me or have any question about mathematics, medical engineering, or we can have a further discussion on machine learning and AI. Yeah, so we can start our journey to the evolution algorithms. As you may know, many artificial intelligence technologies are inspired by our nature, especially biology. So the neural networks are inspired by human brain. So the neural network try to imitate the human brain neurons, and then they try to think like our brain. So while the neural networks draw from the brain structure, there is a whole other side of AI that's inspired by the nature and especially the evolutionary theory, like genetic algorithms, which they encode the solution using DNA sequences. So the genetic algorithms are believed as the real evolutionary algorithms. But broadly said, particle swarm optimization, artificial immune systems, and clonal optimization are also considered as an evolutionary algorithm nowadays. So take genetic algorithms as an example. These algorithms are like watching natural selection play out of a computer, picking out the best solution and move forward and to evolve. It always finds the best or the fittest generation or individual to survive the environment. But for computer programs, so we call that artificial intelligence because we use a computer to simulate the evolutionary process. Then the practice swarm optimization, which always reminds me of watching birds, or flocks, or fish, or fishes, or ants, or bees. They are getting foods, but they try to do that as a group. So they exchange information and always can help each other to find the best solution. So evolutionary algorithms are usually used in solve the complex optimization problems. So there are lots of machine learning approaches we have learned. I think most of us first we learn supervised learning. We utilize a data set with input-output pairs, where each input is labeled with the correct output to train models to predict outcomes accurately. So for the supervised learning, we usually apply in classification tasks and also regression tasks. So for classification, the data are categorized in predefined classes. the outcome will be discrete or either binary or multiple classes. For the regression tasks, as usually used to predict a continuous value. The second machine learning technique we use is unsupervised learning. This technique focuses on identifying patterns, relationships, and structure in data without the use of labeled examples. It's usually used in clustering to group similar items, and also to do the dimensionality reduction, to compress the data or to simplify data without losing important features, and also discover rules that describe large portion of data to find association. So last time, Dr. An gave us a talk for the reinformance learning. That the learning through is a learning through interaction. An agent learns to make decisions by taking actions in an environment and receiving rewards or penalties in return, aiming to optimize cumulative rewards. This technique is ideal for sequential decision-making problems, such as game planning, robotics, and navigation, where an explicit model of the environment may not be available. So for the evolutionary algorithms, it uses mechanisms inspired by the biological evolution, such as selection, mutation, crossover, to iteratively evolve solution to optimization problems. It is particularly suitable for complex optimization problems where the solution space is poorly understood or highly nonlinear, including scheduling, design, and machine learning model optimization. But as far as I know, it seems that the neural network attracts most attention now. So I'll keep this question while we going on the journey. So I think we are quite familiar with optimization problems in machine learning. We usually use gradient descent, right? Yeah. So the minimization in machine learning, we use a quadratic function. That almost exists everywhere because the loss function in a machine learning model is usually defined as the mean square of the difference between the current solution and the target. This kind of function is relatively easy to find its minimum because of two main reasons. Number one, usually there's only one local minimum, and therefore once we find the local minimum, we get to the global minimum. And for the second, we can use the gradient descent algorithm or its variant methods to find the minimum. In gradient descent method, we first select a start point, as we shown here. We first set a start point, and then we move it according to the gradient direction, which means to travel along the direction that the function value reduces fastest with respect to the current location. If we have selected a good learning rate, this iterative process will guide us to close enough to the optimum solution. However, in many other complicated optimization problems, gradient descent does not always work. For example, this figure shows a function that has more than one local minimum. As we can see here, the result of gradient descent depends on where you start. So one of the start point will get into this local minimum, which is not the global minimum, but the other two will, with the gradient descent, will guide you to the local minimum. So that depends where it starts. In some even more crazier situations, gradient descent method will stuck at local minimum fast and won't be able to improve much. Yeah, this here is a showcase. This is a function in the package benchmark. So we will use this function. So usually researchers will use this kind of function to test their method if the methods work well enough. Yeah, this is another crazier situation. And also on the other hand, gradient descent can usually be used in continuous problem, but cannot handle discrete problem directly, such as a network or graph or like combinatory optimization problems. So the search space is always within continuous numbers. In machine learning, we usually handle this headache by using one-hot encoding to convert the categorical values to numerical values before training the model. Feel free to ask me any questions if you have any, and make any comments when you have any.
So Zach, one question. So probably later on you're going to talk about it. But for evolutionary algorithm, do we need to go through the entire process following the order of selection and then crossover and then mutation, or the order is relative that you can switch those orders when you do the computation?
Yeah, I think that's a good question. I never think about that myself, but I think the current process, there is a reason. We may come back to this question again after we go through the optimization or the evolutionary algorithm process.
Yeah,
the audience may not be familiar with all the process. Yeah. So continue the optimization problems. So we have a few key components. First is the function. It may not be as easy as y equals to fx. It can be like a sequence of coding, like process. Like if we want to make a good dish, you first like clean your kitchen and then cut the veggies and then prepare the meals from beginning, right? But generally it's like a function as a process that when you get the input, it will give you the output. This is the optimization problems, and it give you the variables. So usually it's a vector of a few either being binary inputs or continuous numbers. So this is about the variables. In the reality, we also have constraints. Say, so if x1 represents a percentage, it cannot be less than 0 and cannot be greater than 1. And in some binary classification results like true and false, like S2 is only can choose from only from 1 or either 1 or 0. So the feasible solution is any x exists in under the constraint. The optimum solution is that when we solve the optimization problem, we give you the good solution. That is the optimal solution from the feasible solution space. Yeah. So there are also different types of optimization problems, like linear or nonlinear. So usually linear problems are easier, and nonlinear problems are more complex ones. And also we consider about variables inputs either being continuous or discrete. So one example for the combinatory or discrete problem will be the knapsack problem. Imagine that we have a backpack that can hold about like 15 kilogram. And our optimization problems that can we fit as much as things so that the backpack can hold the best value. So like this book, its value is $4, and for this one, $2, $1, and $10, and $2. but each one has different weight and the value. So this is one kind of a typical problem for the combinatory optimization. And also this is a famous traveling salesman problem. So imagine there are like 7 cities in a country, and each city has its location, and between the city, there's a distance here. And imagine that if we have a salesman want to travel from one city and go through all the cities, can we design a best route for him or her to save the traveling time and the tickets, the price? Yeah. So for if we use a brute force search, the number of the solution, or the number the space, the solution space is the permutation. Say if we have 7 cities, the permutation of 7 cities is 360. So imagine that we have 1,000 cities in the world, and we are trying to travel that. So how can we get the best answer? That is a very hard one. To the best knowledge, I know the dynamic programming can reduce this brute force search down to the complexity to n over the power to 2 times 2 power to n. So this is an NP hard problem. So so the conventional method are not good enough or not fast enough to find the optimal solution. So for the solution method, analytic is usually a mathematician will do that to prove the best way for the to generate formulas to do the analytic solution. And also we can do the numerical analysis. So these are computational algorithms that iteratively search for the solution, like a gradient descent. They are particularly useful for complex problems where analytic solutions are not feasible, but that's not good enough for more complicated optimization problems, as we stated here. The last solution method is a meta heuristics. In computer science, the greedy algorithms kind of that. The other one is like the evolution algorithm. They just give you a sufficiently good solution to the optimization problem, not throughout search for the whole space. There are kind of high-level procedures designed. Do you have any question here?
I just want to add a brief comment that the famous traveling salesman problem that some of you may have known a mathematician from Carnegie Mellon University, Dr. Luo, and he I think he is a mathematician, and he's also very passionate about teaching young his adolescents about math. So every year over the summer, he would travel within 1.5 months. He would travel 40+ cities in the U.S., mostly by car, sometimes by airplane. And he always told, I don't know whether it's true or not, but he told us that he every year he needs to solve the travel salesman problem to be able to find the best routes that is most efficient and allow him to cover most cities in the shortest time.
Yeah, that's true. And also when we design the vacation journey, we also have this problem, the very practical problem to solve. Okay, so we can move on to the so when I prepared for the evolutionary algorithm, I always want to think about the best like the real situation in biology that can imitate the evolutionary algorithm. So here's what I find. So in horse racing competition, the rule is relatively simple. just given a distance, and which horse runs the fastest and first reach the final line will win. And the estimate of this game is about 50 billion to the US GDP. So it's like a big event in the world. So on the right hand side, you can see there's this is the horse race line from the very beginning, about 1700. So that to my surprise, that begins only from 3 horses. The horse name are very famous here. Listed here, and the time is about 1700. And all the people, because they always want to win the game, and the prize are very big amount. So everyone wants to get the champion. So either to train the rider, get it faster, or they will like breed the horse to get the best horse and run fastest. So here's a problem: can we select the good horses, and then by breeding different generation of the horses, we get the horse run faster and faster. So here, the horse start from 3 horses, and for each generation, the people always find the good horses, which are winners, or the winner's relatives, to generate the next generation. So they breed more horses, get the female and male horses, best genes from them, and then they will, by doing so, they get the best female and male horses genes crossover. So also during the history, we know the gene mutation will happen naturally. So some surprise will happen when we get the next generation of horse. That may get a better horse DNA. So, and then we run another competition, and we re-evaluate which horse is the winner and get the horse rank. And we always select the best horse to breed the next generation. So this is very close to our evolutionary algorithm. So first we have a goal function, which is like the optimization problem. Here is just run fast and get a champion. And the solution is the horse DNA. I would say who gets the best DNA of the horse will have the best probability to win the champion. So here's the optimization method. They do this breeding history for more than 300 years. So first they initiate for 3 horses, and then they select a good horse to breed. They select the winners and their relatives. They select the good female and male horses, so that we have the crossover of the genes, and the mutation happen naturally. And then they reproduce the horses for next generation, and then they evaluate the horse by the competition. Yeah, and then they repeat for every generation. So if you look at the records from the beginning to now, to our surprise, this optimization method actually works. So on the right-hand side, here's a figure of 3 different competition of the horse racing. So the x-axis is the time starting from 1850 and to the very recent 2005. So you can see that on the y-axis is like the running time. So as you can see, the time is going down. So the optimization, I would say, is pretty interesting, right? Surprisingly, in our history, we can prove in the biology our evolutionary algorithm works. Do you have any questions here or comments?
This is super exciting. And we do see that the curve may not be linear, right? So the decrease of the times tend to, over time reduced, right? So we have a decreasing rate of return, doing this evolutionary selection process. So and then would this be like a general rule that if you reach a plateau, you think, well, no further change in mutation and crossover won't help anymore, and we've already reached a global minimum, so we will stop? Is that the general rule of deciding upon the optimal parameters?
Yeah, in our computer science, that's what we discuss. By tuning parameters, we always can find the best way to get a better optimization solution, right? But as we show here, here's a actual history, and the horse, I think they will die. So for this generation, if they die out, and for next generation, the horses may not be able to beat their parents. So that you can see along the time, sometimes the best runner will have more time running than their parents. So there's a key point in our evolutionary algorithm is that do we keep the parents in our selection? So in our horse history, that never been the case. The horse will die, right? So that's why we have this bumpy and up, down and getting down and then getting up time of trend. But when we look at the larger trend, the time is decreasing. Yeah, so that's the point. We're actually making the DNA better and better.
Mm-hmm.
Okay. Yeah. So evolutionary algorithms are a subset of the bio-inspired algorithm that uses mechanism inspired by the biological evolution to use to solve the optimization problem. So here's some important components of this algorithm. So first is the individuals and genomes. So we call it gene or DNA. So this is similar to our solution. We use each individual to represent a one solution, potential solution in our search space. For the second one will be the population. So as we can see in our previous example, all the horses in one generation, we call that a population. So each horse will be the individual. And for the next one will be the fitness function. In the evolutionary theory, the species or individual will try their best to fit the environment. If one individual have the best fitness within the environment, they will survive and get more resource, and usually they will have more offsprings, and they will get more children, right? So the fitness function evaluates the fitness in the given environment. The environment defined by the fitness, the function itself. Also, the fitness function is a critical component as it guides the evolutionary process. So without the fitness function, we won't know who will be the winner, and we will never be able to bias to the better solution, and we reduce the resource for the the worst solution. So fitness function is a key component for our algorithm. So the next one is selection. It's a process that how to choose individuals from the population to contribute to the next generation. So selection is often based on the fitness function. With the fitter individuals, will have higher chance of being selected. This mimics the natural selection or human selection, where the fittest survive and reproduce. Next will be the genetic operators. The mutation. Mutation will introduce the variation by randomly change of each individual. So that happen naturally in our biology, but in our computer we also manually involve some mutation operation to get rid of the local minimum and try to find the better path towards the global minimum. The next one will be the crossover, or we call the recombination. This mimics I would say the male and female, and then they get together to produce the next generation. So say if we have a good population and we select the good individuals as parents to create one or more new individuals, the crossover encourages the mixing of good individuals, and then this is the mechanism to produce a better solution. I would say the crossover will help the algorithm to converge. Next one will be the generation. So after the selection, mutation, crossover, we will generate the next generation for the evaluation, and then select which are the winner, which are the loser. So also we will need the termination criteria to decide when the evolution the algorithm stop. The condition under which the algorithm start running. That's about the termination criteria. This can be a fixed number of generations. Say if we run this evolution 400 times and then we stop. There's one kind of that. Also, we can define a improvement value. Say how much time we reduce between last generation and this generation. If we have the time increased less than like 5 seconds, we terminate the iteration. We also have the niching method. These techniques are used to maintain diversity within the population and to avoid premature convergence to like local minimum. Niching will allow the preservation of multiple good solutions, especially in problem with multiple optima. So elitism is a strategy that will keep the best individual in the loop. So unlike the horse racing history, maybe the best horse that will die out. But with this, with our algorithm, we want to keep the individual. The numbers will not die out, right? And we can keep the best individual in loop to get into the next generation run. By simulating the process for natural evolution, this algorithm can effectively navigate the complex and high-dimensional solution spaces to find optimal or near-optimal solution to some challenging, like highly nonlinear or combinatory problems.
Zach, could I have one question?
Sure.
So it seems to me that one of the many advantage of using this evolutionary algorithm in comparison to the gradient descent is that we won't have to specify the fitness function. For example, in the horse race, we don't have a explicitly defined fitness function. I mean, we compare the speed for sure, but it seems to me it doesn't depend on the specific organization of the race. For example, you could have as NBA players, right? You can have those 32 teams, and they move, they eliminate and then go to the next stage and play off, etc. Or you can ask all the horses to run at the same time, and just pick the best players. And the selection, the fitness function can be very flexible or even not mathematically defined, but still, as long as you have some mechanism to select players, right? Or NBA teams, for example, right? You can still somehow over time, improve the algorithm. Is that true?
Yeah, I think that's true. So as I mentioned, the fitness function may not be able to describe correctly by a mathematical function. It can be some process of a code to decide which is better, which is not. But in our algorithm, we always need to define a function which give you the input and produce the output.
Mm-hmm. Yeah.
Yeah. So if we do not know what is like A, if we cannot decide whether A is better than B, then we will not be able to run the evolution in the iterative process.
Right.
So that's why we need the well-defined fitness function.
Okay. So it means that as long as you can compare like two, like out of these two, which one is better, then the algorithm will run, right? That's a minimum like criterion we need to place.
Yeah, I guess that's the point. But because in our horse racing game, the competition is not to evaluate correctly for each horse, right? So they have many variants, like soccer game. Sometimes like Germany will win, but sometimes like Brazil will win. But it's a probability. So that's the actual game. But in our algorithm, everything is under control. So we can always evaluate each individual for each generation, all of them. So it seems like we know everything. We stand in a very good perspective, and we know every detail. That's why we can always find the best solution or best candidates for the next run. Yeah.
Yeah. Thank you.
Yeah, thank you. Yeah, that's a good question. So here's the genetic algorithm process. So we start from generate the random population, and each individual here shown here is a sequence of binary numbers. So say if we have 100 binary sequence number, 8 digits number or 7 digit number, either being randomly generated or you have a prior knowledge, you can start from a better starts, right? And then once we have this gene pool, we have this 100 candidates, we will first calculate each individual's fitness function. We get the fitness value. And we usually use the fitness value to inspire how we select this within this 100 candidates. So ultimately, we will gain we grant the reward to the good player, and then we will eliminate the bad players. After the selection, we will get these intermediate results and do the crossover and then mutation and get a new generation. It depends if we have replacement selection or we add on selection. So like in our horse racing game, the new generation always replacing the old generation. But in our because we are programmer, we can always keep the old generation. If they're actually better than the new generations, we can keep them in the loop. So by doing by doing this iteratively, we hope to improve the gene pool to get a better and better population. And then once we reach the combination criteria, we can always find the best solution within the final pool. So that's a strategy.
So Zach, there's a question that Jeremy posted on the chat.
Oh.
Could you answer that?
Yeah, I look at the chat. Could there be bias, or will there be always be only one best candidates? So usually there will only be one best candidate because we have a well-defined fitness function. So we can always be getting one is better than the other. But sometimes, especially in the discrete optimization problem, we'll find a situation that maybe two of those have the same value. Say if we have a class and each of 50 students, and they do the math quiz, they all maybe two of those they get 100 score, right? I cannot tell which is better than the other one. Yeah. So, but for the solution itself, it doesn't matter which one is the best. So usually we'll get only one, the winner. Does it make sense, Jeremy?
Yeah. I was just wondering, like maybe, like when the result, the fitness function give you one best, give you like tie, and you think they're the same, but actually they might produce different results when you like do it for the next round.
So if we have like two candidates, you think they're the best player, we can always evaluate those two players using the fitness function. So there's only three situation we will meet. One is A larger than B, A equal than B, or C or A smaller than B, right? So yeah, so we can always find if A are larger or smaller than B, we can find a better one. If A equals to B, I would say A is equally as good as B.
Okay.
Right.
So it means that you can have equally good but different solutions, right? So you won't have to choose one solution out of all the other solutions. You can have multiple that are as good as each other.
Yeah, yeah, but if you're trying to find your best route, like traveling 7 cities in your vacation, you have to decide which one you want to choose.
Mm-hmm.
So that's the usual situation.
Right.
Yeah, you cannot do it twice.
but whichever you choose, that won't matter, basically.
Yeah, it doesn't matter. Like if you the same price at the same time, I think it doesn't matter.
Okay.
Right. Yeah. If something that does matter, you can always code that into your fitness function. So that's the key problem. That's the key thing. Why the fitness function is so important. Okay. Yeah. So here's a genetic algorithm process. Here's an outline. I'll be going through each of those one by one. So the first thing is the information encoding. So this is all about how we represent the potential solution in a way that the algorithm can work with. So so think of encoding as a translating a solution into a language that the genetic algorithm understand, like DNA in our living organism. They encode genetic information. In our natural, we will have 4 different characters, like A, C, G, T, in a DNA sequence string. If we do that in our computer to calculate the DNA, we can encode those as like 0, 1, 2, 3. So this is like encoding. So the common encoding strategy will be the following: the binary encoding, like 0, 1, in the snack pack problem. Either we get this item in the bag or no. So this is a binary encoding. We also have the integer encoding, like DNA sequence. We have 4 integer numbers as encoding. And also we have real number encoding. Say if we have the temperature, we have the pressure, we have the like height, etc. So why encoding matter? The way we encode information will directly impact the efficiency and effectiveness of the genetic algorithm. Like poor encoding will lead to longer convergence time, even failure to find optimal solution. For example, in the knapsack problem, the order of the item does not matter. Say if we have this green book and the blue book here, and we pack that in our bag, it doesn't matter if we collect the green one first or collect the blue one first. So if we encode this problem, a solution to this problem as a list, the order that does matter. So the blue first or the green first will be the different solution, but that's not the case. So in this problem, we prefer to use a set, which will where the order does not matter for this problem. By using the set structure, we can eliminate the permutation complexity before solving the problem. So that's why we need a good strategy to encode our solution. And also, whatever encoding we choose, we need to be ready for evolution. It must allow for meaningful genetic operation like selection, crossover, mutation. The encoding will be the first step. So next one will be the selection. This is where the actual magic of the survival of the fittest comes into play in the world of algorithm. They will choose the best candidate. So think of selection of a natural inspired audition. So from the potential solution we have, we'll need to decide who gets to move on the next round, right? So kind of choosing the best candidate for a job. So the goal is to pick out the individuals or solution that are most likely to lead us to the optimal answer. But without the fitness function, we will never know. So that's why we usually we evaluate the candidates using the fitness function to provide information for our selection decision. In theory, we will keep the best genes to pass on the generation. So first, we will evaluate every individual and then get a fitness score. It will tell us how each solution is performing based on the criteria. Now there are a few different ways we can go about the actual picking process. So the first one will be roulette wheel selection in a casino. So imagine we have a wheel like this, but instead of the numbers, each slice here, each number or each color here will represents in each individual in the population. But here we will have an even or a bias area of the wheel. So for the better player, we will have a larger area of the wheel so that we can find the better candidate. So the process is random. But the fitness will the process is random, and then we will take the individuals by its probability defined by the fitness function. So this is a roulette wheel selection. The second one will tournament selection. This is more like a mini competition, like soccer game or basketball game among a few randomly chosen individuals. They compete through a champion game. So this selection method will increase the randomness because the best solution may not be always win because we have the randomness here. The last one will be rank selection. We'll sort out the population based on fitness score and select based on rank. The higher rank, the better chance we got the selection. But it balances out the lower rank individuals still have a small probability to be chosen. So we have two strategy for selection. One is to keep the parent generation. The second one we will not keeping that. If we choose not to keep the parent generation, we will think about how we keep the best solution in the past generation. This is called elitism. So it is good to have a mechanism to preserve some candidates that lose in each evaluation and selection round. That's a crucial balance that drives the evolution process towards the optimal. So this is a selection.
So Zach,
So
one question. Yeah, for the different selection method, are these three methods ordered by the increasing order of randomness?
No. Yeah, that's not by the randomness. Those are just three commonly used selection methods.
Okay, so because down the road it should depend on the weight assigned to each candidate.
Yes.
And so the roulette wheel is going to be the probability of selecting a candidate would be proportional to the fitness score, right? So basically,
yes.
Is say on 100% scale that someone has a fitness score of 2 is going to double the probability of being selected compared to a fitness score of 1. Whereas the rank, presumably, I think the rank would work differently because if you have 4 candidates, your rank would last 1, 2, 3, 4. I'm trying to think of the in terms of proportion, what is difference between the rank and the roulette? Which one give more equal proportions, while which one give more discrete or different proportions? Is there a systematic difference between these two?
I don't think they're really different because they are all randomly selected during the process. So for the rank selection, they just give you the rank, but even so, the lower rank candidate may also be selected. There is still a possibility, but may not be proportional to the fitness function. They can there's a different way to weight the fitness function.
Right.
Yeah.
Okay, great, thank you.
Yeah, so the crossover will create the offsprings. So here are different crossover methods. So usually the one-point method is that we find a point and then exchange on the rest. Is a one point. We can also do the multiple points crossover. For the second example here, we only select in the middle. We exchange those two genes. And also we can have a uniform crossover. We can randomly select a few index of the vector and then do the crossover. So that's a different strategy, depending on different method, different problem. So the goal is to gambling on new combination and hope that we can have a better next generation in the fitness performance. So here is a diversity is the key. We will keep the gene pool diverse so that we can always keep the opportunity finding a better solution. So for mutation part, we introduce a randomness to avoid getting stuck. So once we get the local minimum, by using mutation, we can sometimes even though it's a lower probability, we may get out of the box and get off the local minimum and go to another path towards the global minimum. So give you the opportunity getting avoid stuck. So for the mutation, we usually change a little bit, so we won't change a lot, right? And usually we assign a low probability. Also, the mutation keeps the genetic pool diverse, and also generate new gene in our pool. So here are some mutation strategies. So the binary encoding, we can do one mutation. For the real number encoding, we can add the standard normal. We can add the Gaussian mutation. Like if we have a number of 1, we can add a number, random number subject to the Gaussian distribution. When we design the mean value and the standard deviation. We can also swipe the integer or permutation encoding. So those are 3 different mutation strategies. So the mutation is like the trading off between overfitting and underfitting. This is a parameter we need to tune. We do not, if we choose a too small mutation, we will not be able to get out of the local minimum. But on the other hand, if we get a too much mutation, the algorithm will not converge quickly. So here are some tuning strategy. Here, so we have already covered encoding, crossover, mutation, and selection. So survivor selection is about whether we keep the parents or not. So these are the tuning parameters or strategy we can do with the parameter of each step. So I have been thinking about why the neural network get more attention in AI rather than the evolutionary algorithm. So on the left-hand side is a neural network, and the right-hand side is the evolution algorithm. So here's the analog, optimum function, encoding, and how we update, and how we get the convergence, and also how we get out of the local minimum. We introduce some variation. So the EA and NN, we have a similar component, but why and a neural network get more attention? So I think that's because the neural network is data driven, and also the input for neural networks data, but for the evolutionary algorithm, the input is environment or the function with a constraint, which is like the fitness function itself. So the neural network give you the model. Model is a result, right? But the evaluation algorithm will give you the optimal solution, give you a vector which best fit the fitness function. So so for the strategy, neural network learns from the data. The evolution algorithm will survive in the environment. So the neural network will do the task a human can do. So I will say in our current trend, neural network will gain much more attention than the evolutionary algorithm. Yeah, I think so. For the evolution algorithm, in the future, I think they can be used with as a complementary region component with the neural networks. So here there's a trend that they apply the EA in our machine learning to speed up the optimization, but this is kind of new. Okay, so so let's the time. Well, the time is going fast, so let's go to some hands-on with the package. Okay. Okay, I will share again. Okay. So I hope you can see my screen now. So I'll be using this package called DEAP. The package is a platform to enable us to quickly prototype the evolutionary algorithm. So here we use a 1max problem as an example. So the 1max problem is that we have, let's go to the fitness function here. So if we have a vector of like 10 numbers as an individual, the fitness function here would be the sum of all the individuals. Each individuals can only choose from either 1 or 0. So this is simplest question, but that is the optimal solution would be all 1, right? As we human can easily find the best solution in 1 second, but for the computer, they may not know at the very beginning. So first step is to install the package, and then import the tools we need. So for the package, first we will create the Phoenix strategy. So here we are trying to maximize the Phoenix function. Here's a creator.create. After create the strategy, we will also create the individual. So this is just to give you the handle of how we get the individual, but not actually assigning the first generation of individuals. And then the package allow you to get a few tools, and this is the toolbox. We get a toolbox, and then we collect a few tools within our toolbox for the later use. So we first to assign the Boolean numbers for each individual's component. So here we say for each entry of the vector, we can either choose only 1 or 0. For each individual, here is to get each individual. We repeat initial repeat times, and then we create the individual. So now we have 100 individual as a one population. So the same population again, we do it. And here is the important thing. We use a list as our coding encoding data structure. And then here's the finite function definition. So we define the evaluate function using the finite function, and the mate using the two prongs crossover to get the next generation. And then we have a mutate. Here's a mutation strategy. We flip by bit. And then here's I forgot what's this parameter represent. Probably is the probability. Yeah, the mutation probability. And then we do the selection. Use the Tolman selection. Here's a Tolman selection parameter. So in the main function, we first is select the seed, the random seed. Get the initiation population. We have 300. And then here's how if we keep all the current and the parents and the next generation. Here is yes, and then so here is we what we keep to show in our log. So we have the statistics of the population. We have the average standard deviation, mean number, and maximum number of each population. So simple enough, once we decide all the step function, finite function, the crossover, mutation, selection strategies, ready to go for the algorithm iteration. So here's the code running. May take some time. Okay, along the generation, we can see the maximum is always increasing. And then at the 35 generation, it reaches the best solution, which is 100. And below is the plot for the generation versus the fitness score. We can see it's increasing trend. So do you have any questions?
Yes, I do have some question. The first is about the diversity, the genetic diversity you mentioned, like within the population. You mentioned like using the niching function. I think it's like put maybe the first generation population into several subgroup and do the parallel computing. But is that like if you maintain the diversity, will it affect or lower the algorithm's efficiency? It's the first question.
Yeah, I think you get it correct. If we keep the diversity, the evolution will go, but the convergence process will be much more slower, because we always want to try something new. Yeah.
Like, do you have some idea on like what level of diversity is enough for this diversity population?
I think yeah, that's a good question. That's something similar to the parameter tuning our machine learning models. So that will depends on the fitness function and depends on your encoding, and also depends on the algorithm itself. So this is a kind of art rather than science, I would say. You have to like try different numbers. Like if we change the crossover probability from 0.5 to like very low, if we choose it number 0.1, let's see if we go as far as previous, we can try. So basically also like, so now if we do reduce a crossover probability now, even we have 40 generation, we will not get the maximum to 100. So they will get it slower, right? So if say if we have a 0.8, let's see how it performs. Yeah, this is like the art of parameter tuning. Yeah, when it goes to 24 generation, you once hit 100.
Yeah.
Yeah, so you have to try different things. For some complex, more complex finite function, I would say you need more generations, and maybe you need more a crossover probability, and also the mutation probability. Yeah, but it kind of hard to define or decide which one is better.
Yeah, thank you.
Yeah.
And another question is about like regarding the gene mutation and recombination. For this hands-on algorithm, you choose the mutation and the bit flip mutation. But you also mentioned like the golden mutation, other mutation, and other like recombination. So how do you choose this, like what mutation you need to use, and the evolutionary algorithm, or run randomly, or are based on can be based on certain specific genes, for example, certain genes, or maybe certain chromosomal variations are proven to be related to specific characters, specific disease, or that you need to put more emphasis on that kind of mutation and to get a better result, or better horses in your previous example.
Yeah, in our horse example, that's purely biology. We human have no control on their DNA. We just try by luck. So but in our coding, I would say the mutation strategy will first based on how you encode the problem. So for this specific problem, the solution is either being 0 or 1, right? So so we can the choice very limited. So the Gaussian mutation is not the case, because there's the solution space is only defined on 0 or 1. It's binary. So that's why we can either use like the flip bit, or like 1-point crossover, multi-point crossover, or permutation encoding. But here, as we pointed out, the evaluation function is the summation of all the each component of the vector, right? So actually, if we encode it carefully, we can use map here instead of list. Because list, the order of the numbers are important, but the set, the order of the encoding vector does not matter. Yeah. So here the permutation mutation is okay, but it won't change if we use we try to optimize the one max function. Does it make sense? This way, the first element and second element, we exchange it, we have the same result of summation. Yeah, so here the flip bit will be the good choice.
I see. Yeah. And the last question, I'm sorry, I have so much question. It seems like mutation, recombination, these are really essential parts of this algorithm, but I'm thinking that you are talking about the applications in other areas, like in machine learning or in other areas. But how to like apply this method to this area, since there are no like the genetic mutation or recombination problem?
So for the application of the evolutionary algorithm with our current machine learning method, I think that's an open question to the researchers and to the public. They're still in research, and I personally don't have a good idea or perspective how we can incorporate this algorithm with the neural network or a supervised or some unsupervised learning. But that's an open question to the public. So for the question you're asking about the questions, so evolutionary algorithm is particularly used in combinatory problems, because say if the first dimensional vector is either 1 or 0, the second will be the number from 0 to 1. So that's even a mixture of a real number and a categorical number. So in those problems, if we have a optimization problem, evolutionary algorithm will be better than commonly used neural network, because it will fit this problem better. But if you use much more resource for the neural network, I bet the neural network will outperform the current evolutionary algorithm, because you don't think the resource, or you have unlimited resource, right? Yeah, so that's a trade-off. So for given resource you have, which method you will be choosing. So that's a trade-off.
Yeah, thank you so much.
Yeah, I have a similar question. I think probably similar to Yuyi's last question. I'm thinking of one application for the evolutionary algorithm is to replace regression analysis, at least not neural network, but traditional regression analysis that we care a lot about, feature, for example, feature importance, coefficients. And we can probably easily replace the coefficients with some real numbers in your vector or your set, right? Because the order doesn't matter. And then the objective would be the outcome, the target, either a binary prediction or a house value, for example, continuous variable. And then through the computation, you'll be able to tell which coefficients are more important than the others. If the non-significant coefficient would be reduced to probably close to 0, others would be magnitude larger. Have you seen such applications, replacing regression analysis with evolutionary algorithms?
I personally don't. I've never seen that, because like this evolution algorithm is to solve, like as I mentioned in the PowerPoint, is to find the best solution or to find the vector itself. But for the regression problem or neural network, it's trying to build a model. So that's a different approach or different aspects of the solution. One is to get a tool like neural network. You get a good tool. You give me an input and I'll generate output. So it's like the neural network is trying to imitate the function itself. But on the other hand, the evolution algorithm is trying to give you the results. the function itself is well defined. So that's kind of different aspects. Yeah.
Yeah, interesting. Yeah, so yeah, I know I don't know that enough to tell. Yeah, but it's interesting to see though. But your perspective that they are more of complementary to each other, right? I could think of you could use this algorithm for hyperparameter tuning.
Yes.
And it's probably going to be more efficient than traditional grid search or random search, right?
Yeah, that's the active application in the machine learning field. Yeah, parameter tuning.
Right.
Yeah.
Yeah. Any other questions from the audience? Okay. Yeah. Thank you so much, Zach, for this really very informative talk. I learned a lot from the talk, and we really appreciate that. You are a mathematician. So presumably you could talk a lot about mathematical equations or algorithm that no one of us understand. But you go with this really step-by-step explanation, starting with intriguing examples, especially the horse racing, which is eye-opening to most of us, and link that so well to the evolutionary algorithm. So we could understand, and then you provide this worksheet for us to play with, especially I think the DEAP package would be really useful if we want to try out the algorithm ourselves, but without really going much into the algorithm itself, playing with at a higher level. So personally, I really learned much from this presentation. It may easily take me probably 10 days or 20 days just to learn the basic, but I now I feel I'm more confident, a lot more confident before, in saying something about the algorithm. So thank you so much for your presentation, and I see that you make a lot of efforts to make this presentation interactive and practical. So truly appreciate that. And next, in 2 weeks, we are going to invite our very own Jingyi. And Jingyi Huang is a doctoral student at Shanghai University of Sport. And she is working with me on some really exciting research projects on disinformation, misinformation regarding COVID-19 social media posts. And she has some, I would say, really breakthrough in identifying and correcting misleading news articles pertaining to COVID-19, thanks to the application of the RAG framework that we talk about, the retrieval augmented generation framework. And she has assembled a huge vector database from peer-reviewed articles to evaluate the biases in social media posts pertaining to COVID-19. So in 2 weeks, I think she will be in good shape to present the research. So stay tuned. And thank you again, Zach, for your wonderful presentation. Thank you everyone for coming to the space to spend your very valuable 1.5 hours over the weekend to learn something new. And hopefully we all learn a lot from today's presentation. So we'll see each other in 2 weeks. Thank you, Zach. Bye.
Thank you all. Bye-bye.